Okay.
Recording.
I've got some symbols I want to hand out to you guys. That's the first thing we're going to go over here. So, the name of this class is Electrical Circuits, and that's what we're going to focus on. And our primary focus will be on schematic diagrams. Schematic diagrams are often called ladder diagrams because they resemble a ladder with two power bus bars. Everybody get a syllabus. And they have, just like a ladder, they have rungs of circuits. We also will spend some time on regular wiring diagrams, which are typically what we call picture diagrams. Both of the diagrams give us valuable information, but the schematic helps the technician out a lot more once he learns how to use it. So we want to begin with talking about circuits, and everybody in here should have had ACR122 Principles of Electricity and passed the class, but you learned a lot about circuits, and that there were about 4 or 5 different types. The first is what we call a simple circuit, and that's what we're going to start with, from basic electricity, a simple circuit. And a circuit, an electrical circuit, is pretty much defined as an electrical concept which will control electrical energy in a useful manner. When we look at any circuit, there are some basic requirements. There are 3 basic requirements. The first is to have a working circuit is we need a source of power. Whether it be a battery, an AC generator, a DC generator, your local supplier of power, we need a source. Second, we have to have a path for the electrons to flow through this circuit. Okay? And then finally, we have to have a load. Everybody get a chance to sign this? Everybody get a chance to sign? Great. Thank you. Now, we may have multiple loads. We may have more than one path. Sometimes we may have more than one source. But we have to have at least one. So before we go any further, let's make sure we understand path and load. The definition that we're going to use, and you have to tell yourself, you can ask yourself every time on a load to determine if it's a load, you got to say, does it consume electrical power? In other words, does it use electrical power to do useful work? Now, useful work is a loose term. We think of things like providing light, that's useful, or providing heat, or creating an electrical magnet, this kind of thing, or inducing electrons to flow in an inductive circuit. These are useful, but electronics uses a lot of useful purposes that we wouldn't think. They may have a circuit and have a solid state component, electronic component, that uses 4.3 volts. That's the way it was designed. That's what it does. And so they'll put a resistor in the circuit that will use the rest of it. Okay? And so we go, well, that doesn't seem very useful. That is, because it made the circuit work, okay? So that's what you got to ask yourself. Does this item consume power? You know, like if we have everything, we've got a source, we got a path, and we stick, say, a crowbar in there. It's going to consume power, but it's not going to be useful. It's going to blow up the circuit. So when we looked at our circuits for basic electricity, we started with what we call was a simple circuit. So I'm going to say, I'm just going to draw a simple circuit. I've got L1 bus bar. That's a power source. And we're probably best known for, say, 115 volts AC. And a second power source that I'll title L2, line 2, the bus bar. That's just a conductor that we can get the power from. And it's also 115 volts AC. All right? And if you took your meter and you read across it, that would read 230. If you read from one item to ground, it would read 115. So I have my first component. I have to have a source of power. Everybody see that? 230 volts AC across. All right. Let's say my load. How about a light bulb? Does a light bulb consume electricity? Does it do useful work? Yes. So I don't see many of them that use 230 volts, but nevertheless. So I have a load. Now I need a path, which in most cases is going to be a wire, right? That is a simple circuit. And we define it as a simple circuit because it only has one load. Okay? Now the next thing Brian probably taught you in basic electricity was we have a lot of simple circuits, but we also have a lot that are what we call series and some that are parallel. Now I've got two loads in this circuit, right? This is done. I have a source, I have a path, I just happen to have two loads. This is called a series. It goes through one, then the other. Now we learned a lot about, in basic electricity, the laws of these circuits. And so let's just take a look at that. My law, let's say in a series, voltage. In a series circuit, and why do I call this a series circuit, John? Because there's more than one load, right? And one path. There's nowhere else for the electrons to flow. One path. If I had one path but only one load, we call it a simple circuit. So, the voltage. I got 230 here, don't I? That's considered voltage T, total voltage. And hopefully this is just a reminder of what you and Brian did in basic. How does the total voltage in this series circuit, what are the rules? Well, it's all additive. The voltage from 1 plus the voltage from 2 would equal the 2. And so now these two share the voltage of 230. Okay? Whereas if I had one, it's getting all of it. If I got two, they're sharing it. And you go, well, how do they always share it? Half? No. Based on their resistance. In other words, if this thing has, say, 500 resistance ohms, and this one has 500 ohms, they're shared equal. Does that make sense? If not, though, it's going to be some percentage. What about this? What kind of circuit is that? Series circuit. If I have more than one, and there's only one path, it's still a series circuit. I don't care if there's 100. But if there's only one path and more than one load, and so now it would go plus the voltage from the third load, plus the fourth, plus the fifth. However we have, they share the voltage. Okay? All right, so this can be very important to us, and this is what we use series circuits for in HVAC and air conditioning, is mainly for safety and control circuits. And we'll get into that a little more depth. Now, we also have some more rules, okay? So I think y'all probably covered 4 main topics that are of interest to us. We have current, right, amps. We have resistance. And we have wattage, right? Although I think y'all probably used P total. Right? Actually, y'all know what the difference between using an E and a V and a P instead of a W. You know what that means? It means it's theoretical. If you see it written in a formula and they write V and A, that means this thing's based on they went out and did it. Whereas if I use this, it just means it's theoretical. So it's not a big difference. But anyway, same thing. Voltage, my current. All right. This is very helpful. I have a series circuit. Remind me to get your name and get you the sign the sheet afterwards. I've got a 3-load series circuit. In a series circuit, we know that voltage is shared based on their resistance. But what happens to my amperage? Well, the amperage in a series circuit is all the same. In other words, how can we do this? Light bulbs usually, we use wattage, don't we? So let's make this one 1,000 watts. This one's 750 watts. And there is no math in this class. This is just concept, guys. And 500 watts. These things are using different watts, so they're obviously going to have different resistance. But the amperage in a series has got to be the same. Okay? And so we'll come back to that. But that's very important. The amperage at 1 has to be the same as amperage at 2, has to be the same as amperage at 3, and so on and so on. So in other words, let's say I put a 10-ton compressor here and wire it in series with a light bulb. The 10-ton compressor pulls 50 amps. The light bulb would normally pull 1/10 of an amp. We're going to have 50 amps flowing through here. It's going to be tough on a light bulb. It's going to burn pretty bright for a millisecond. Okay? Our resistance, what's the rules with our resistance, y'all? Y'all remember that from basic? It's additive. Resistance from 1 plus resistance of 2 plus resistance of 3. Look familiar? Same thing with my wattage. Wattage of 1 plus the wattage of 2 plus the wattage of 3 all adds up to my total wattage. So, we've got voltage we've got wattage, so I would just simply add these up. 1,000, 750, 1750, and 500, what's that? 2250. Total wattage is equal to 2250. Is that what we just said? All right, and so y'all learned your two pie charts, right? E over I times R, and P over I times E. Who's got a calculator? Or pull one up. So if I know the wattage, which is 2250, I know the voltage, don't I? So if I divide 2250 by 230, that will give me my amperage. Okay. 9.78. I'm relying on y'all. All right, so this rule tells me what? That the total's 9.78, then we're pulling 97.8 here, we're pulling 97.8 here, and 97.8 here, okay? Whoever had the calculator, let's go ahead and finish this up. All right. E divided by I, right, should give us my resistance, right? So 230 divided by I, y'all said was 9.78. That's going to give me my total 23. 23.51. And then, of course, we can figure out total resistance by putting it in here. 230. No, that's what I just did, wasn't it? Yeah. That wasn't. We already knew that. So total voltage was 230. I'm sorry. Y'all said that was 23.5. Okay, and so that's the total circuit. And we could look at the circuits each here, here, and here. But there's a common theme running through here, y'all. Additive, additive, additive. Series. Amp draw is the same. Amp draw is the same. Another thing is, if there's on a series circuit, what happens if there's an open in the circuit? That's right. That's what makes it a good safety and a good control. Nothing runs unless we have everything in order. And for safety, if anything opens up, cuts it out of the system. Now let's look at a parallel circuit. Start with our simple circuit, right, y'all? So a parallel circuit means I have more than, I took it off, I have more than one load. Because one load means it's a simple circuit. But if I have two loads and more than one path, so I'm just going to come down here. The electrons can flow in more than one direction here, right? They could either go this way and that way, so they will. More than one path. Can I have 3, 4, 5, 10? That's a parallel. Now, parallels presents us with some nice attributes. There's resistance. We got 3 rules. All right. We said the one thing that stands out was what over here? In the series is our amps, all the same. over here, voltage stands out. 1 is equal to 2 is equal to 3, etc. In other words, if I have a 230 total, this one's getting 230, this one's getting 230. Let's not overlook the fact that in air conditioning or HVAC, that many of our loads, they're big loads, like condenser fan motors, blower motors, compressors. They require a voltage of 230, something big. If we put them in a series, if I put a condenser motor and a compressor, they got to share it. And they weren't made to work off of 73 and 142. They were made to work off of their rated voltage. So most of our big loads are going to be wired parallel. So this is what stands out, because this is all the same, isn't it? It's all additive. Plus, 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 watts, plus, plus, plus. Now this is a little different. Y'all remember this? This is the last time I'll go over this. I think it was, anybody remember the formula? 1 over R1, is it times 2 over R2, something like that? Is that how y'all remember it? It was, no, it was.
Just one time.
Now the R3 is a really good one. It's the reciprocal of R total is equal to, oh, that's the one, R1 plus, pardon me, R2. A little complicated. I'll tell you what these two mean right here. Look, we're not engineers. We don't sit there and calculate what the resistance should be. That's not our job. But whenever we're in a parallel circuit, we know this about the resistance. It will be always, the more I add, the lower it is than the total. In other words, if I have 5 items, it's not additive. You don't go this one plus this one. It's always less than the total. Like if 1 is worth 5, the total is going to be less than 5. It's always less than if it was just 1. And so we base almost everything off of this and this. Okay? Okay, that's enough about circuits, I think. Okay, now, so we discussed simple circuits, series circuits, parallel circuits, and of course, lastly, we can have a combination. We can have a series parallel, or we could have a parallel series, right? Something like there. Is this parallel? Yeah. But this one is what? Series in here, and vice versa. We can have that too. So it's our job to recognize and sometimes design circuits that will get what we want done. Is this a circuit? Does it do useful work? If it works, does it have to happen? I'm done erasing. The 3 essentials. And it's got one other thing. A switch. Did I ever put a switch up there? Because it's not essential. It's very useful, but it's not essential. Let me ask you this. The whole point of this, and the engineers, the manufacturers, is design stuff to make the air conditioner or the heater, the heat pump, or whatever we're using, work efficiently and conveniently for us. Everybody agree with me? Oh man, come on. So I got a 115 volt, like in that wall plug, right here. I got a 115 volt circuit to control these lights. I got a design. You see that switch back there? Flip that thing. They both work, right? Somebody had to sit down and go, how can I design a circuit where that would be useful? So somebody doesn't have to walk the clear other end of the hall to cut them on or cut them off. Now, we can look at it like in most of them, a single row switch. Right? There's my light switch. You shut it, you have power to the load, we have light. So most people have, that's pretty simple. But I got another switch there. Now what happens? You go, it wouldn't work if we both told that's no good, right? That won't work for us. That's your homework right there. Design me a circuit that'll work for a two-way switch. Now, they got 3 ways, 4 ways. Let's see if you can do that. All right, I want to talk about this here. Before I do though, this is out of your book. Take one pass along, please. Yeah, the voltage will always be the same, which is what we want, because most manufacturers either say, look, this is manufactured to operate, they guarantee to operate if it'll operate plus or minus 10% of 230 or something like that. And so that thing has to have 230. It wouldn't work off half the voltage or a third of it. So take one pass. What was assignment A? Begin reading chapter 40, right? So then B and C, I'll look that up before we go. We'll have to write it down on there on when it's due, okay? It's on Blackboard. We'll look it up before we get off. Or any of the others left? B. Did anybody get the C? Did C make it as well? Did everybody get the C? But I gave just enough. Now I'm getting to it. I'll pass these. Lab A is on top. Take one of those. Lab B's at the bottom, take one of those. So you have an A and a B on your labs. Okay. Get this up together here. Now those assignments I pass out, they're in your book. And there'll be a due date I give you. But that way you don't have to rip it out of your book. You know, later on you go, I still have this, you know. I don't mind you doing it in your book. It's your book. Do what you want. But with this, you can turn, because I need one turned in. That way you can keep yours and turn this one in. All right, so that passes around basic concepts of electrical circuits, complete a path of electrical current and any necessary elements, a closed circuit and an open circuit. The only difference is the electrons will not be able to flow in an open circuit. Must have a path, must have a source, must have at least one load. And by the way, these PowerPoints are on Blackboard under the button PowerPoint. You need to see it. I know I go fast. So here I have a little circuit, 120 volts. You plug it into the wall. So there's no on and off switch. When you plug it in, it's complete. You've completed it to the source. Over here I have an electric heater. That's my load. Pretty simple. We just went over series circuits. And here I have a series circuit, L1 to L2. We're reading 208 across from it. Did you have a question, sir? Okay. And here, do y'all know what that high pressure switch is? That's a switch that would open if we sense high pressure. Same way with a low pressure, but sense low pressure. And a thermostat will open on a set determination of the temperature. But if this path continues, it'll wire this electric motor. That's a series circuit. Nowhere in that circuit can the electrons flow in two paths, right? There's nowhere for it to flow in two paths. So we call that either a simple circuit or a series circuit. What did I say? These are all part of the path. They are switches. Does it matter if I have 1 or 100? No, it's still low. Still low. Now I tried to illustrate this. See our rule, total amps, that's supposed to be a T. I don't know if you remember. Amps at the first load, second load, it's always equal, right? We talked about those. Parallel path, more than one path for the electrons to flow. Most loads operate from line voltage in our industry. And here is a depiction of it. I've got a 120 volt source. The electrons, when they get to this point in the circuit, can either continue, and they will, and flow down here to the first load. Here, once again, they can flow in more than one path, right? Thus, the determination that it's a parallel circuit, right? If the electrons can flow in more than one place. And we looked at parallel flows. We look at our amp draw here. It's additive here, not equal like we saw in the series. But the voltage is the same, right? Nope, that's wrong right there. I don't know why they wrote that. Total voltage is equal to the voltage at 1, which is equal to 2. So whoever made that, I didn't make it, Justin. But that's wrong. It should be equals in here, right? I hope y'all know that's the key. In a series, amps are equal in every load. In a parallel, voltage is equal at every load. Okay, that's the big difference. Now here we have a series of combination on this is what we call a ladder diagram or a schematic. I have L1 and L2, that's hot leads. They don't tell us how much voltage, but we know there's a voltage difference across here. Here I have a rung or a circuit with an open switch, right? And it goes to some load called CFM2, which is defined as, okay, condenser fan motor 2. Condenser fan motor 2. Get down to the second circuit. I have a low pressure switch, a high pressure switch, a temperature switch, and a load labeled C, which I assume is compressor. No, take that back. Contactor. Okay, contactor. Now, this load labeled C controls any switches labeled C. So you see how this is labeled C? Now this open set of contacts is labeled C, and so is this. So when this energizes, this is going to make this close and this close, creating a path for the electrons to flow to the compressor and the condenser fan motor 1, okay? All right, key terms, great. We'll go over those a little bit later. So, did I give everybody the symbols? Did I hand that out yet? Yes, sir. All right, let's look at these symbols. I thought I had them loaded on here, y'all. Sorry. I'm blackboard. Sir? No, did I give everybody one of these?
Yes, sir.
You didn't? Okay. Anybody else? Let me look around, make sure I don't have it on here. There we go. All right, I guess before we start, these are the kind of definitions to be on your first test. Symbols and loads. Okay. Can y'all read this? Load. An electric device that consumes electricity and does useful work. A motor. Y'all probably familiar with motors, right? Okay, a motor is an electrical device that consumes electrical energy. It's used to rotate a device in an electrical system, right? So I tell you what, we'll do these after the symbols because it'll make more sense. All right, the first one I have up here is a temperature switch. We may see a temperature switch inside of a thermostat. Right? Temperature switch. And also, this senses temperature too. So we have a lot of different types of temperature switches. Does everybody recognize what this is? I'm going to pass it around. Although that's a single. That's a single. Single throw, single pole switch. That's what we're looking at. It's a switch that's closable, right? I labeled it L because most of the time you use it for light switch, although you could use it for anything as long as you didn't want over the voltage rating that it could handle or amp draw. Could have drawn it here. Not a difference yet. But when we take a switch like this and we add a flag to it, this is known as a flag. Okay. That's a temperature flag. That means the first switch was said light, it's manual. This one opens and closes based on temperature. Now here it does matter. Think about this thing here. This switch, if the temperature rises, what's going to happen? We might want to do this for air conditioning. I set it. It's too hot in here. Click. Bring on my air conditioning, right? Now look at this one. As the room cools, what's going to happen? Click. It'll close. I might want to use that for heating. But at any rate, y'all see the difference. Just think of it. When the temperature comes up, what's going to happen to this one? It's just going to continue to open. Okay? All right. Temperature switch and a flag, and we'll see 4 or 5 different flags. I don't know if these are in order, y'all. Thermal overload. All right. I've got double pole throw on mine, right? Is that what y'all got next? Let's just talk about that for a second. All right. If this thing closes, I have one path for electrons to flow. Does that make sense? That's considered a pole. If I can energize one path at a time, then that's a pole. So this would be a single throw, single pole switch. What if I did this? Keep it right. What if it's this way? I got one pole, right? If I throw it, I got one pole. So it's a single pole. But how many throws do I have? So this is a double throw single pole. Does that make sense? What about this? All right. How many throws do I have? This thing's open and shut. Right? This is open and shut. I may not draw it right, but it can't go up and meet. Okay? So it's single throw, but when it closes, how many circuits can I energize? So that would be single throw, double pole. Does that make sense? When this thing closes, one throw to close them. Some kind of armature bridge in there. Now I got 2 circuits on, so that's double pole. If I had 3, triple pole, right? I got a single pole, single throw there.
It says a single throw.
Single throw, that's right.
The other one is a double throw.
Yeah. Now, how about this? If I can ride over it a little bit. What we got here? So I got double throw, click, 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 click. See, they're tied together, click, 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 click. So that's a double throw. And how many poles? 2 poles. Here and here, or here and here. A little confusing, just want to make sure y'all understand that. Now he said something, I think it was you, or he said something about your light switch here. Did everybody see that light switch going around? All right, so it had you could connect power to one end of it. Connect power here, or here. Let me throw it open. How about that? You know, it's open. You connect power here. I'll give you this for your homework. That switch is not like that. That switch and that switch look like that. What's it called? Double throw. Okay, so at least you know you're going to need that in the diagram, right? Okay, now what we got? Thermal overload. All right, a lot of our equipment, especially if you had basic refrigeration, you probably came across the word hermetic, which means hermetically sealed, welded shut, maybe semi-hermetic, bolted shut. any way you want to look at it, our compressors with electric motors in them are not serviceable. I don't mean you, I guess you could get your torch kit out, cut it open, and work on it, but I mean, they're disposable, you know. We make more money swapping than we do repair. So a lot of our stuff has to be done where it cannot be serviced. And it can't have a spark. In other words, when you open and shut a contact, there can be a spark from it shutting and opening. We can't have that in an atmosphere of refrigeration gas. And so we have what we call thermal overload. I'm going to pass this around. This is a condenser fan motor. Non-serviceable. Goes out, you replace it. I got windings, I got run windings and star windings. Right up here on the top, when it comes by you, you'll see it's a little translucent tape. There's a little silver rectangle. That's it. Okay? Take a look at that. Now, what does that do? When it gets too hot, and the way it's going to get hot, y'all, is from electrical amp, the current. Electrical amps not only will kill you, they're really hot. Most people who have electrical shorts and get electrocuted get serious burns. Very hot. That thing, although we say it senses heat, it really senses the heat from the electrical amps, okay? So if this thing gets too hot, it's going to open up and try to protect the motor from hopefully let it cool off, okay? If you see this in a circuit and it's pulled apart, that means it's overloaded. This is not something we reset manually. We don't take the top of the compressor off and reset it. It should reset. If it doesn't, it's a dead duck, okay? Everybody got the symbol? Okay. Y'all got it. First test, y'all got to memorize these symbols. So we've got the temperature switch, thermal overload. Now, fusible link, I probably ought to take off. We just don't see it anymore. We'll get to this, but I used to have one I couldn't put my hands on. This is a heater. We'll flow electricity and amps through this heater. It'll get red hot and give off heat. That's what strip heat is. Used to, in the older days, where this wire comes into the porcelain, we would put a fusible link, right? That's what we're on right now, fusible link. Now you go like, well, you know, I've heard of a fuse. And y'all, this symbol is the one that gets missed. There's two of them, a fuse and a fusible link. Most people miss that on the test. 2 humps up, 1 hump down, right? Now what does this do? Is everybody familiar with the fuse, kind of? This is similar except for when it trips open, there's no reset. And it is soldered. Are y'all familiar with the term soldered? Take a soldering iron and it's wired in. It's not like a wire connection. It's at about 400 degrees, molten metal puts it in. And so we used to put it, or they used to put it in places where if they put a fuse, a customer might go in there, know just enough to be dangerous, and put something else in there and try to reuse it again. And so we had these fusible links, so you had to know what to do to take that out and repair it, and you knew to go looking for why did it trip in the first place. So a fusible link is something that they want an expert to look at if it blows. Does that make sense? All right. No, I don't think that's what we're talking about here. I'll see if I can find one. But these look, they just look silver, and they have wire coming out both sides of them where you solder them up. All right, I just said this was a heater. And that's the symbol for a heater, right? And you don't go, well, Clay, you had 4, and this time you had 5. You know, there's no exact, just kind of up and down, right? Kind of straight up, kind of like, I don't know, lightning or something. But anyway, now, this is a heater. We know what a heater is: a load that consumes power to produce heat. What is a resistor? Anybody know? It's a load, absolutely. A resistor is just an electronic circuit that it does create heat, but it consumes electricity for us to make the circuit work. Okay? Split phase motor. All right, this is a little. All right. The motor that's going around back there, where y'all looked at the overload, that's a type of split. Did you have a question? I'm sorry.
Yeah, you got single phase.
Did I skip one here? Okay, it is. Man. Let's see if I can explain this. All right. Over at the plant, Alabama Power, they generate power. And you had never looked at it. A generator, electrical generator, very, very similar to a motor. And the laws of physics tells us that if I rotate a metal conductor, magnetic conductor, in the middle of a magnetic field, and y'all should have touched on magnetic fields and basic electricity, right? We have, some people call them north and south, some call positive and negative. Everybody plays with a magnet. It has sides that repel, sides that attract. Okay. Laws of physics. If I rotate this, whether it be by steam or water or nuclear power, whatever, this rotates inside of this magnetic field, this flux field. It'll make electrons flow. So if I wrap me a conductor of wire across here, I just create electricity. Just that simple. Okay? That's single phase power. I created it at one time. Now, everybody familiar with geometry, like if we start here, that quarter is called 90 degrees, 180, 270, 360, right? Y'all follow? And so this power is only generated when we're lined up. So the power works on a 360 degrees. When this thing's turning, when this thing lines up, it turns up. There's 90 degrees or a quarter of a circle. Then it goes back to nothing, right? Goes from here to here. Then it goes the other direction, P. And then it comes back to nothing. So I have, 90, 180, 270, 360 degrees in this cycle. They turned it one time. And turning at this speed, at this exact time, is called single phase power. I've generated it. That's great. We got electrical power here. However, they're already paying to turn this, right? They built some mechanism to turn it. So, if I took a second magnet, and built it at an angle directly different from it. Does that make sense? This one's hot here, or maximum strength. This one here, I still got one conductor spinning, right? That's what they do. And so, when this one's peaking, this other one's peaking here. That makes sense? That's single phase power. They're giving us two hot legs, 180 90 degrees angle difference. Okay? All right. The difference is we could have multi-phase. In other words, more than two. And more than likely, unless you're in a very industrialized area, you're going to get three-phase. You're not going to get 4 or 5. But you can put as many around here as you want. But they take three-phase and they put those, 120 degrees from each other. Does that make sense? These are 90, but we have 3 magnets at 120. That's called three-phase. So anyway, when you see this, what we're talking about is I have one, this is called coil, one magnet using a hot leg, another coil magnet using a hot leg. So this is a single phase, and I think on yours it may say split phase, right? Is that what yours says? No, this one says split phase. Yours says single phase. Same thing. Y'all with me? Single phase and split phase means the same thing. Means I have 2 magnets working in there. When that came around, when this motor came around, you might not could have told it. I want to take a second look. Can you see that separate set of coils? One sits back, one sits forward. That's what we're doing. There's 2 sitting. I don't mean like 1, 2, 3, 4, 5. They're all the same one on the inside, all the same one on the outside. There's multiple, but there's 2 different coils, okay, working at the same time. Y'all welcome to look at that. One's a little bit different than the other. Split phase motor, okay? The important part is 2 coils. I didn't draw that very well. A thermistor. Is that what we got next? All right. It shares its name with a resistor, right? So it's electronic, solid state part. Now a resistor has a set resistance of ohms. About 10,000 ohm resistor, 40,000 ohm resistor. A thermistor is a special resistor where its resistance changes. Maybe it goes from 10,000 to 40,000 based on what? Temperature. We may have one where the resistance goes down when the temperature goes down. Or vice versa. We could have a temperature where its resistance goes up when the resistance goes up, right? Or we could have one inverse. When the temperature goes up, the resistance goes down, okay? Those are called positive and negative coefficient resistors, okay. What, split phase motor? Oh, I got capacitor. Is that on there? I think I skipped this one. Okay, we'll come back to it. What do y'all see on the 3-phase motor symbol that's different than the single phase? Yeah, because there's 3 coils. Y'all see that? There's 3 actual magnets, 3 coils instead of 2. Connector, what's that, y'all? Some kind of connector, wire connectors. You may see something like this, plug connectors, just stuff that makes it easier for us to work on the equipment, right? Connectors. Single pole, single throw. I've already talked about that, haven't I? A single pole switch. Ground connection. I don't even know why we have that in here. We don't have to put that in. Now, a capacitor. This is a capacitor. This is a start capacitor. Probably got a run capacitor. Is there anywhere I'll make this mess?
Really?
pass this around. This is a start capacitor. I'm going to grab a run. And a run capacitor. Do you see a difference to begin with? What's the first difference? Bigger, but okay, that's just the capacitor. What else? That one's black plastic, this one's metal. Alright, think about it. A run capacitor is filled with liquid. A start capacitor is filled with solid. A run capacitor runs anytime the motor's running. So if the compressor runs 10 hours, this runs 10 hours. It has to dissipate heat. And so it's metal, The other one, the start capacitor, only comes on for a millisecond to get it started, and it cuts off. So it doesn't have to dissipate heat. And so whenever you do one of these symbols, a capacitor symbol, you have to write on there what it is. Is it a run capacitor? Or is it a start capacitor? It'll be up to you to label it. Okay? Now some of you going to say, well, I still don't know what a capacitor is. If you looked up in the back of your book, probably going to say something like it's an electrical storage device, which is technically right. Although somewhat vague, it doesn't really help understand what's going on, does it? So let's talk about that for a second. We'll end there. Okay, so I said a motor, electric motor is off. It's a lot like a generator, just in reverse. Instead of you got motion, you turn it into electricity. We take electricity and turn it into motion. So, it will take us a rotor, conductor, magnetic conductor, and give them maybe does everybody know how to create an electric magnet? You take an iron core, you take a source of power, you run the power through it, and it creates a magnet. Ever done that with a nail and a battery? Take your battery wire, wrap it around the nail, and pick up paper clips. So that's what we do. When this power source comes on, you have a certain number of windings around this iron core creating a magnet. Here I have another magnetic conductor. And so it's either going to push or pull depending on how it's sitting, right? That's what happens. It's either going to be attracted or repelled by this thing. Okay. And this same thing I can have on this same leg of power, I could have 5, 10 on it. It doesn't really matter. Okay? That's a non-split phase motor so far. Because a split phase or a single phase motor has 2 windings. Now this motor here, y'all, works great. It just can't get it started. Won't start. So they've come up with different methods to start. This is one of the methods. See this coil in here? I don't know if you can see it when I pass it around, but underneath here, copper wire, which which is not bared. It's actually covered in very thin enamel. So the power goes through it, not across it. And it hooks to it. So I got this little spindle here. Just like this, single phase that spins it, if it doesn't know which way to go. We can't very well come by here and go, because this is what we call a locked rotor. It's not spinning. I can flip it that way, run good. Flip it this way, it should run good. And so one of the methods is what we call a shaded pole. These are considered poles. This is a positive pole right now, right? And that's a negative pole. See this clip over here? I'll pass this around. See this copper conductor? That's a shaded pole. Now, what we do here, and this is a very cheap motor to manufacture, but it's not energy efficient, and it doesn't have much torque. Y'all know what torque is? Starting power. Once it's getting spinning, it just might do good in the back of the refrigerator. You can put your finger probably in that fan. If y'all seen fans, you put it in there, you cut it on, won't hurt you. Now, I'm not saying get it up to speed and put your finger in there, but you know, it doesn't have, you can hold it. You couldn't hold one of our fan motors, our PSC motors, it'd rip it out of your hand, or they got that much torque. So what they do here, let me draw this magnet like this. This magnet, once we cut it on, it creates magnetic flux fields. Y'all might have seen this. Does that make sense? All around it. That's what pulls and pushes this thing. We take a band on here, a conductor there, it creates an additional flux field. And so by banding it, tells it which way it wants to roll. So that's one method. But it's inefficient as far as energy consumption, and it doesn't have much torque. So we have developed, or the engineers, I should say, not me, split phase motors. Split phase motors. So I have another pole over here, y'all. Take my power. I don't know where I'm going here. There we go. So now I've got two sets of magnets, but there's a big difference. My first one, I'm going to call, in the industry we call main, but we usually call it a run. The wire is a certain thickness and a certain length. Now we should learn from basic electricity that conductors, a thick conductor is better than a thin conductor, right? In other words, it conducts electricity easier with less resistance. And so if I have me an electron race, what's going to happen here? These electrons are going to finish before these electrons, aren't they? Does that make sense? We're racing electrons through here. This one becomes positive and negative before this one does. This is out of phase with this. And so I have a push-pull, and I lock, and the other said, then they push-pull. That gets it spinning. We get out of phase. All right, so
With a smaller wire.
smaller wire, because right, it's harder has higher resistance, harder to get through. If we looked at this on a chart, We can say positive, negative on our first one at a time frame of 0 getting started, and we would lag it with our start winding, right? Our second auxiliary winding, it might be here in time. It's out of phase. Now, anyway, this is not the motor class. We have to understand something. We want the farther out of phase, the more starting torque this thing has. So we take a capacitor and we put it in a can. We run power to it. And inside of here, we have electrolyte fluid. And then we have a conductor, like a little piece of tinfoil. And then electrolyte fluid, and a piece of tinfoil, and so forth, all the way in. So that electricity, that electrons, hit the conductor, and then they're slowed down by the electrolyte. Hit the next conductor, slowed down. It causes it to be farther out of phase than the run one, okay? So that's what a capacitor does. Yes, it stores energy, but it discharges it too. It's getting us out of phase. All right, let's stop there and talk about these labs. If somebody would mark that we stopped on capacitor symbol, okay? Well, let's look at this due date. Assignments. All right, B, November the 2nd. The lab, that assignment I gave you there. I'm sorry, not the lab, the assignment. So you won't have to tear it out of your book. And see what's the next one's the 9th. Y'all see that? All right, so write that on the top, because I blacked it out on your two assignments, B and C. Everybody said that B and C, assignment B and C, due to me that day, or those 2 days. All right, did everybody get the lab? Do I have any lab sheets left?
Yeah, I got an extra.
Okay. So everybody got 2 labs. Y'all, these are not due today. Give them today. Do not wait till the last week. You're like, I need to do my labs. But, I mean, they're not due today. And this is how it'll work. You'll put your name on your lab. I'll watch you do it, or I'll have somebody watch you do it. I'll sign or initial it. You keep up with it until near the end of the semester when I take them up. And go, no, Clay, I turned them in. No, I don't take them. You can't turn them in until I ask for it. That way I don't get blamed for losing them. It's up to y'all to keep them. It's y'all's responsibility. Everybody understand? All right, so out here on the trainer, just this side, make sure the power's off. I went by and make sure it was off. We got 6 trainers out here with disconnects. We want to use those disconnects. I highly recommend that you make sure that it's off, no power. And with it, we want to wire up on the first one, I think it's the lab A, we want to wire up a contactor. Okay, now, if you look at a contactor, this is a typical contactor here. Coming out of the disconnect, you're going to find the load side. Power coming from the inside of the cabinet, wired to it, that's their line side. The 2 wires where you can hook to and a ground, we're not worried about the ground, is what we call the load side. Because it's wired to the electrical loads. Remember, consumes power, does use work. You're going to get you a contactor, and on most of these contactors, it's going to say either on the two coming in, it's going to say line or load. That's kind of a big word. And so a lot of times they will abbreviate it with L1 and L2, which means line 1 and line 2 for pole 1 and 2, and T1 and T2. T1's across from L1, and it signifies load. Okay? And so L stands for the line side, L1 and L2, or L3 and L4, whatever you got. And T stands for load, right? And so I want you to wire up, and I think I said red and black pipe wire from the disconnect loads to the contactor line, right? L1 and L2. Now, that's lab 1. Pardon me, lab A. Lab B would be from coming out of your contactor, and you don't have to do it at the same time. It can be two separate labs. You take a contactor. Coming out of your contactor, you're going to wire up to a single speed condenser fan motor. If you need help finding one, we'll look for one. Just as it's shown. Common, run, and the start using a run capacitor. Using red wire on the run and the start. Let's use black wire on the, isn't that what we did on the first one? Black on the common, yeah. Any questions about this lab? Now this would be considered a picture diagram, or what somebody might call a wiring diagram. This is not a schematic, okay? All right, y'all. Any questions before I log off here?